Welcome to episode 90 of your CySA Plus Prepcast. Today, we are exploring remote code execution threats, one of the most dangerous classes of vulnerabilities in modern cybersecurity. These threats enable attackers to remotely execute arbitrary commands or malicious code on a vulnerable system. Often, without authentication or user interaction, the impact of RCE can range from data compromise to total system takeover, making it a top priority for security teams and a critical concept for your CySA Plus exam preparation. By mastering the causes, detection methods, and mitigation strategies related to RCE, you equip yourself to defend against one of the most damaging techniques in an attacker's arsenal. To begin, let's define remote code execution clearly. An RCE vulnerability occurs when a flaw in software, application logic, or system configuration allows an attacker to execute code on a remote device or server. This code can be crafted by the attacker and executed without direct system access. RCE is not simply unauthorized access, it is the ability to run code of the attacker's choosing, which can alter system behavior, extract data, or install further payload. Such capabilities elevate RCE vulnerabilities to the highest levels of severity in most vulnerability scoring frameworks. These vulnerabilities are considered critical because of their potential for complete compromise. An attacker who exploits an RCE flaw can often gain the same level of control over a system as an authenticated administrator. This includes reading and writing files, modifying system configurations, creating user accounts, installing malware, or establishing persistence mechanisms. RCE frequently results in privilege escalation, lateral movement, and the ability to pivot into more sensitive areas of a network. From ransomware attacks to espionage campaigns, RCE is a common initial access vector. RCE vulnerabilities emerge from several categories of underlying software flaws. Common causes include input injection vulnerabilities such as command injection, deserialization of untrusted data, insecure file handling, and memory corruption issues like buffer overflows. Many RCE exploits stem from improper validation of user input or failure to properly handle dangerous data types. Analysts must investigate these root causes and evaluate applications for weaknesses in how data is processed, passed to system calls, or executed in runtime environments. Once an attacker discovers an RCE vulnerability, they use it to deploy a malicious payload, either as a standalone command or as part of a multi-stage attack. These payloads may install backdoors, retrieve additional tools, modify logs, or connect to external command and control servers. In many cases, the payload is delivered in obfuscated form to evade detection, and analysts must be able to deconstruct these payloads to understand their behavior and implication. Common malware types delivered via RCE include ransomware, cryptominers, rootkits, and remote access trojans. Analysts regularly encounter RCE vulnerabilities in high-value systems, including web applications, enterprise platforms, and network infrastructure devices. Vulnerable components often include remote administration utilities, content management systems, third-party plugins, open-source libraries, and default configurations in public-facing software. Since many of these components are widely deployed and difficult to update quickly, RCE vulnerabilities are frequently exploited by automated scanning bots as well as targeted attackers. Public exploits are often released within days of discovery, increasing the urgency of mitigation. Cloud environments and IoT deployments are especially susceptible to RCE threats due to complex integrations, external-facing services, and sometimes insecure update mechanisms. Analysts must assess whether cloud instances expose administrative APIs, outdated services, or webhook endpoints that process untrusted input. IoT devices, many of which lack security hardening, often ship with exploitable firmware vulnerabilities or misconfigured communication protocols that can lead to remote code execution. To identify RCE vulnerabilities, analysts rely on a combination of automated scanning and manual analysis. Tools such as Nessus, Qualys, and OpenVAS scan for known RCE flaws based on software versions, configuration signatures, and CVE data. For web applications, Tools like Burp Suite and OWASP Zap test for dynamic execution points that may be influenced by user input. These tools simulate malicious payloads and evaluate how the system responds, enabling detection of potential execution vectors. However, automated scans do not always confirm exploitability. To validate whether a vulnerability can be exploited in practice, analysts use penetration testing frameworks such as Metasploit. These tools allow the safe deployment of test payloads against controlled environments, verifying whether commands are executed and what level of access is achieved. Metasploit modules are regularly updated to include recent exploits, making it a valuable resource for replicating attack scenarios and refining defenses. Staying informed is a key component of effective RCE vulnerability management. Analysts continuously monitor vulnerability feeds, security advisories, and threat intelligence reports for newly disclosed RCE flaws. High-profile vulnerabilities such as Log4Shell or Apache Struts issues demonstrate how quickly RCE threats can evolve and spread. Analysts use this intelligence to assess their organization's exposure, prioritize patches, and anticipate attacker behavior. Emerging exploit campaigns often reuse known techniques, making historical awareness a powerful defensive asset. Finally, comprehensive documentation underpins every RCE mitigation and response effort. Analysts document identified vulnerabilities, exploitability assessments, remediation timelines, affected systems, and potential business impacts. These records are used to inform patch management, compliance reporting, and executive communication. By maintaining this level of documentation, organizations ensure transparency, improve future risk assessments, and reduce the likelihood of repeat vulnerabilities appearing in updated systems. For more cyber-related content and books, please check out cyberauthor.me. Also, there are more security courses on cybersecurity and more at baremetalcyber.com. Preventing remote code execution vulnerabilities begins with secure software development practices that address the underlying causes of exploitability. Analysts advocate for rigorous input validation to prevent malicious user input from reaching execution contexts. Every external input must be treated as untrusted and evaluated using allow lists, proper encoding, and type checking. Secure memory handling, including the use of bounds checking and safe data structures, helps protect against memory corruption issues such as buffer overflows and heap exploits. Analysts also ensure that developers follow secure deserialization practices, avoiding insecure object deserialization, and unsafe reflection mechanisms in application logic. The use of safe programming languages and libraries can also significantly reduce the risk of RCE. Analysts promote adoption of memory-safe languages such as Rust or Java when applicable, and recommend the use of secure frameworks that abstract away dangerous operations. Modern development environments often offer built-in protections against insecure system calls and include libraries that enforce safe parameter usage. By using proven, well-maintained libraries and frameworks, development teams can avoid introducing low-level vulnerabilities that are commonly exploited for remote code execution. Effective patch management is a cornerstone of RCE prevention. Analysts prioritize the deployment of security updates that address critical RCE vulnerabilities, especially for systems exposed to external traffic. Timely patching significantly reduces the window of opportunity available to attackers, particularly when exploits are published shortly after vulnerability disclosure. Analysts track patch availability using vendor feeds, vulnerability databases, and internal asset inventories to ensure that no exposed systems remain unpatched. In large organizations, automation tools are often used to deploy patches consistently and verify compliance across distributed infrastructure. Network security technologies play a key role in detecting and blocking RCE attempts. Web application firewalls are configured to identify known exploit signatures, such as payloads attempting to inject commands or exploit known URL patterns. Intrusion prevention systems provide an additional layer of defense by inspecting network traffic for signs of command injection, shellcode, or anomalous traffic originating from internal systems after exploitation. These technologies enable analysts to stop RCE attacks in progress and generate alerts for incident response workflows. Segmenting the network is another critical defensive strategy. Analysts isolate vulnerable systems or applications into separate network zones to prevent lateral movement. If an RCE vulnerability is exploited, the attacker's access is limited to a tightly controlled environment without access to production systems or sensitive data. Network segmentation is enforced using internal firewalls, VLANs, or microsegmentation tools that restrict communication based on predefined policies. This approach reduces the blast radius of any successful RCE attack and helps contain threats more effectively. Securing system configurations also helps minimize RCE risk. Analysts ensure that default services are disabled, unused components are removed, and file and process permissions are tightly controlled. Administrative interfaces are locked down to known IP ranges or protected with multi-factor authentication. Analysts verify that systems do not run with unnecessary privileges, minimizing the impact of an RCE exploit even if it occurs. These hardening techniques eliminate many of the secondary vulnerabilities that attackers rely on after gaining initial execution. Regular vulnerability assessments and penetration testing are indispensable. Analysts use scanning tools and hands-on testing to identify exploitable flaws before attackers do. These assessments go beyond surface-level scanning, probing deeply into application logic, third-party components, and custom business logic for potential RCE paths. Penetration tests simulate real-world attacks, helping analysts understand how an attacker might chain vulnerabilities or move laterally within the environment after initial compromise. Monitoring is essential for real-time detection of exploitation. Analysts configure system and application logging to capture command execution events, unexpected system calls, process creation anomalies, and outbound connections to untrusted destinations. These logs are centralized into security information and event management platforms where they can be correlated and analyzed using behavioral rules. Indicators of RCE exploitation often include unusual network traffic, persistence mechanisms, or the appearance of unauthorized administrative tools. Rapid detection enables fast containment and remediation. Training is a key part of maintaining analyst readiness. Analysts undergo ongoing instruction in secure coding techniques, RCE vulnerability research, penetration testing frameworks such as Metasploit, and incident response to remote execution attacks. Training includes case studies of historical RCE incidents, reverse engineering of public exploits, and hands-on simulation of mitigation strategies. This continuous learning ensures that analysts remain capable of defending against an evolving threat landscape and can provide timely, informed responses to new RCE vulnerabilities. Lastly, thorough documentation underpins every aspect of RCE risk management. Analysts maintain records of detected vulnerabilities, patch status, penetration test results, network segmentation plans, and monitoring configurations. These records are used during audits, compliance checks, and post-incident reviews. Documentation also supports long-term risk reduction by tracking trends, identifying recurring issues, and reinforcing secure development standards. By systematizing RCE prevention and response, organizations ensure continuity and accountability across security teams. To conclude, Episode 90, remote code execution vulnerabilities represent some of the most dangerous threats cybersecurity analysts face today. They allow attackers to take full control of systems and are often used in targeted attacks and widespread malware campaigns. By implementing secure coding practices, maintaining effective patch management, using protective technologies like firewalls and intrusion prevention, segmenting networks, monitoring for suspicious behavior, and training security professionals, organizations can mitigate these threats before they cause harm. Understanding and addressing RCE vulnerabilities is a critical part of your CySA Plus exam preparation and central to building a resilient cybersecurity program. Continue applying these practices as you advance in your analyst journey. Thanks for listening. To learn more about cybersecurity, please visit baremetalcyber.com. There you will find best-selling books, videos, and even more free cybersecurity training courses. Please subscribe to the Prepcast and our various podcasts. And thanks for listening.